In this video we are going to introduce the Smart Greenhouse application, explain how it is structured and give you a demonstration of how it works. This application is meant basically to monitor some relevant parameter for the vegetable growth and through the usage of external platforms visualize and process the data in order to control the actuators in the greenhouse modules. The Smart Greenhouse is composed by different actors: the devices, to which are physically connected the sensors and the actuators, a platform as a service ThingSpeak, a ThingsBoard, the catalog, and Telegram. Every actor communicates with the others only via web. Let's talk about the catalog. It is a central actor in the overall application, and it's of fundamental importance for the cooperation among the user interface and the other actors. It is composed by two elements, a text file and a RESTful API. The text file contains all the relevant information about the overall application that are used mainly by Telegram. More in particular, the file contains three groups of informations: the endpoints, that are the URIs that the user uses to visualize the ThingSpeak channels pages, the ThingsBoard pages, or the webcam services. The device list that contains all the active devices in that particular moment, and for each device there is a sublist called resource list that contains information about the active sensors and the actuators of that particular device. To maintain this list updated, showing only the active devices and resources, the catalog cleaner makes use of the timestamp. If the device or the resource has been posted more than 2 minutes before the check, then the catalog cleaner removes it from the list. The user list contains information about all the users registered to the application service. The RESTful API is the way through which it is possible to interact with the text file. This interaction is allowed only via web through the usage of the CRUD methods and using JSON data format for the payloads. Let's focus now on the first device, the Raspberry. A number of sensors and actuators are connected to the Raspberry. In particular, we have a gas detection, air temperature and humidity, light intensity, and a camera, while the actuators are a fan, a water pump, a heater, and a sprinkler for the air humidity. In order to implement a microservices architecture, every resource is associated to a Python script. All the scripts have always the same structure, made up by two threads. The live thread is used to update the catalog through the usage of the post and put methods. The second thread performs the real action of the resource. The sensors send the measured data to ThingSpeak and ThingsBoard every specific time interval using MQTT communication protocol. The actuators get the action to be performed by doing a GET request to the related ThingSpeak channel field, and so they communicate using HTTP communication protocol.
The last two components related to the Raspberry Pi device are the LCD display and the camera. The LCD provides an immediate interface of the main measurements of the greenhouse. It communicates with the sensor microservices through MQTT. The camera provides a live streaming through a web service of the greenhouse to remotely monitoring the status of the plants. Both LCD and camera have been implemented in a second Raspberry Pi due to practical reasons. However, it is possible to connect them in the same Raspberry Pi where the sensors are implemented. The next actor in the system is Arduino Ethernet Leonardo and Arduino adapter. Arduino is used to actuate and control lamp and to get measurements from the moisture soil sensor. We have chosen to connect the moisture sensor to Arduino because it was the only way to collect exact measurements. Arduino has an Ethernet port that makes it able to communicate over the internet. The board communicates using MQTT protocol. The central component to make Arduino working correctly is the Arduino adapter. The adapter can be implemented inside whatever PC and whatever Raspberry Pi, supporting the Mosquito broker. The adapter communicates through MQTT with Arduino board, using the Mosquito broker, and with ThingsBoard, using ThingsBoard broker, and with ThingSpeak, using ThingSpeak broker. The adapter receives lamp control commands from ThingsBoard and forward them to Arduino board. In this way, I can change the brightness of the lamp according to the needs of the plants. The communication is bidirectional because Arduino publishes the moisture soil measurements to the adapter, which, in turn, delivers the measurements to ThingSboard in order to update the user interface with the current value of the soil moisture. At the same time, the adapter publishes the measurements to ThingSpeak in order to provide the last measured value to the control strategy for the activation of the plant watering system. The adapter provides also the functionality to subscribe the Arduino board to the catalog through REST communication. The adapter receives the alive message every 2 minutes from Arduino board, meaning that Arduino is active and it is providing the services, and consequently subscribes the device and its resources to the catalog. All the information are exchanged in JSON format. The last faculty provided by the adapter is the lamp brightness control using Telegram. The communication with Telegram takes place using Mosquitto Broker MQTT connection. When Telegram takes control of the lamp, the control from ThingSboard is deactivated and the user interface is updated with the new control type. The difference between the two types of control is that from Telegram we can send just few values of brightness, while using ThingSboard I can choose the brightness between all possible values, as shown in the demonstration.
Let's talk now about ThingSpeak. Its role can be described in 3 phases. The sensor measurements are published on a channel field. In our case, we have 2 channels. In the first are stored the data of the temperature and humidity, and in the second are stored the data of the soil moisture and the light intensity. The second phase consists in the usage of this data. For each of the 4 measurement fields, there is a script implemented through MATLAB analysis that basically computes the average of the last 10 data, and comparing it with a threshold value decides whether turn on or turn off the related actuator. These algorithms run every specific amount of time. In the third phase, the results of the control algorithms are published on the related channel field and becomes available for the actuator scripts.
As we can see in this case, the measurements of soil moisture are published on ThingSpeak every 2 minutes. Instead, the pump script compares them with the threshold value every 10 minutes. Once a dryness is detected, the pump will activate for 5 seconds to water the soil, but in any case, the monitoring of soil moisture is still guaranteed every 2 minutes to reactivate the pump 10 minutes later if needed.
ThingSboard is an open-source IoT platform providing cloud technology. We have used the free version. ThingSboard is used to create a user interface of the entire greenhouse using 2 dashboards. The first dashboard is the monitoring greenhouse. There, one can visualize all the current measurements collected by the greenhouse devices. The communications between the devices and ThingSboard occur using MQTT connection through ThingSboard Broker. The information are exchanged in JSON format. The second dashboard is the control greenhouse. There, one can control in real time the brightness of the lamp using a special widget, the knob control, that sends remote procedure calls containing the desired brightness values to the Arduino adapter through MQTT. In the same dashboard, one can have a feedback about the current status of the lamp, whether it's turned on or off, and which is the current brightness of the lamp. In addition, one can have information about whether a Telegram control is activated or not. The great power of ThingSboard is that one can control the brightness of the lamp and can monitor the system everywhere, even if one is not connected to the LAN. In order to make the platform operating faster, it is possible to implement ThingSboard locally using Docker containers. However, in this way, ThingSboard operates only in the same LAN of the greenhouse. The IoT greenhouse offers the possibility to switch between these 2 implementations of ThingSboard. In the demonstration, it has been preferred to use ThingSboard implemented in the cloud.
Focusing on the user interface of the system, we've developed also a Telegram bot that allows to interact with quite all the devices connected to the system in a simple way. First of all, you have to sign in into the Smart Greenhouse and log with your credentials in the Telegram bot application. We've developed a specific web service that exposes a web page to sign in, adding a user to the catalog file. This page is composed by a fillable form asking personal information like name, surname and email, and user information like username and password. Pushing the sign in button at the end, your information will be added to the catalog, as you can see in this case for Rossella. If a user tries to fill the form with an existing username, like in this case, the system replies with an error message and the user is forced to change the username and recompile the form. Now, if we try to access in the Telegram bot with the credential registered right now, the bot will ask first your username and then your password. If you mess up your password, it asks you to rewrite it. Once you're logged in, the bot shows a menu with various buttons, from sensors and actuators to device list and delete users. All the functionalities of the bot are accessible from that menu. In particular, if we press the sensor button, we can ask for information about all the available sensors, like temperature, humidity, gas presence, heater status, and so on. If a sensor is not currently connected and you try to obtain information about that sensor, the bot replies with a "sensor not found" message. Then, with the back button, we return to the main menu. About the actuators, we can activate and deactivate the fan whenever we want with the respective buttons. The brightness of light is also controllable with another submenu that allows to set discrete value from a maximum to a minimum of 40%. The light dashboard provided by Thingsboard indicates when the Telegram control is activated with the proper panel Telegram status activated, and in this case is not possible to vary the brightness from the dashboard knob. If we press the Return to Knob Control button instead, the Telegram control is disabled and the brightness can be set turning the knob. Also, the graph changes due to the level of brightness. In order to see the graphs from ThingSpeak or Thingsboard dashboard, we can press the associated buttons and obtain the respective links. Each of them is referred to a particular channel in ThingSpeak or a dashboard in Thingsboard. In this case, for example, we've opened the temperature and humidity channel from ThingSpeak and the overall dashboard from Thingsboard. Furthermore, we can ask for the list of connected devices registered to the catalog in order to have an overall view of the system. They're divided into two lists, one for Arduino and the other for Raspberry. We can ask also for the link associated with the camera inside the greenhouse that gives us live images. Finally, you can delete a registered user indicating its username. In this case, for example, the bot will provide to erase Rossana's info from the catalog's users list. Otherwise, if we insert a wrong username, the bot replies with a user not found message. All the communication are performed with REST and MQTT methods. In particular, the Telegram bot communicates with ThingSpeak, retrieving data from channels, searching info about channels from the configuration file and doing a proper GET, so with the RESTful method. It communicates with Thingsboard, publishing via MQTT in several topics, and with the catalog, again through a RESTful communication. Finally, the sign-in is performed with the POST method.